Yes, so why we came here to the European XFEL is the question of how quickly do electrons move in a molecule from one place, from one atom to another atom. And the molecule we picked for this is acetic acid for several reasons. Acetic acid is interesting, of course, in a lot of areas, but in particular it features two oxygen atoms that are in slightly different places with slightly different neighbors. So formulating the question a bit differently is, at what time do oxygen atoms in a molecule actually find out they are not isolated atoms, but they have a different chemical personality in the molecule based on their surrounding atoms? And so what we try to do to see is to pump with light, intense X-ray light here from the machine, one oxygen atom, and to see how quickly information from this one oxygen atom travels to its neighbor oxygen atom that we can probe then with another pulse, another attosecond pulse that one can make here now at these machines at the other atom. And a lot of things had to come together because FELs, pretty much all FELs have the problem that pulses are generated in a statistic fashion. So one had to bring together a lot of measurement technology here to realize this experiment. Not only measurement technology, but also the teams that operate these different technologies. And this was the key thing of this experiment.
Yeah, since we are interested in the very fast energy redistribution dynamics in this molecule, this is where we came here to the European XFEL in the first place, because this has very precise, very short pulses, attosecond X-ray pulses that can be controlled in a to a very high degree. But then, of course, we need to measure the response in the molecule, and this happens exactly here at this detector at SQS. That can measure at the very high repetition rates, at megahertz burst mode repetition rates, the spectra in high resolution here with the Gotthard 2 detector, and also the temporal resolution, the temporal structure of these pulses with the angular streaking in the cookie box. That's the detector that we see here on the back. So this comes all together and measures the molecular response at the high repetition rates, which is very important for the statistical analysis that we need to perform then later to understand the very fast energy redistribution dynamics in this molecule.
So the timescales on which energy flows in molecules is interesting because it controls the dynamics also of how molecules react chemically, so how they would do a chemical reaction, for example. And people generally in our community want to currently find out on the fastest time scales how this chemical reactivity changes by, for example, pumping or changing the molecule on one end. How does it change chemically on the other end? So how quickly does this energy flow through molecules? And of course, acetic acid is only one representative of this larger class of organic acids. So it is also, in that case, of general appeal. What we will find here in this one representative will be interesting and inform research on other molecules. And the other interesting thing is, of course, if we understand these quick flows of energy and excitation in molecules, who knows, at some point we can even use this information also and the control of this information, once we understood how it works, to do, for example, even things like computation on very fast timescales on molecular levels in very small systems and extremely fast. So to build maybe in the future a very fast quantum computer, for example.